Welcome to this tutorial covering your first steps with the UDOMORE Depth Ocean plugin to Petrel. UDOMORE Depth is for stochastic velocity and structural depth modeling. This plugin makes depth conversion fast and efficient. It has strong value for reservoir structure modeling workflows. In this video, we will explain how to prepare input data in Petrel, create and configure UDOMORE Depth scenarios, select outputs, and visualize them in Petrel. Let's first run through data preparation in Petrel. To run UDOMORE Depth, you need to have 2D seismic time interpretation maps. The following optional input data is also handled by the plugin. Well tops, which must be available as a stratigraphy to the relevant horizons, and 2D seismic interval velocity maps. Now your data is ready in Petrel, so you can get going with the plugin. We're going to run you through two scenarios. One scenario with default velocity model parameterization, and one scenario with custom parameterization according to your existing knowledge of the field you're working on. We'll conclude this tutorial with a comparison of the two scenario outputs. So let's start with scenario 1. To create a scenario, go to the Scenario Edition pane and enter a new scenario name. Now you've created a scenario, you can start configuration. The first step is to define layering. The second step is to upload your input data into the plugin. The third step is to select your interval velocity functions. This is a choice you make, for example, based on previous analysis of well velocity profiles. On the first layer, we'll use a constant velocity. On the second layer, we'll use a seismic velocity. On the third layer, we'll use a linear compaction with depth. At this stage, notice that the plugin offers prior parameter values in blue, which are set by default. Also notice that the plugin reacts to prior parameter values by offering post parameter values in orange. The post values are computed using our Bayesian co-kriging algorithm and corresponds to the best possible estimations of your interval velocity function parameters. The fourth and final step is to verify the performance of your velocity model in terms of well depth mismatches. UDOMORE Depth provides two types of interactive control tools: crossplots and depth mismatch statistics. In this table, notice that well depth mismatches associated to the post parameter values have been minimized by the plugin. Following these four simple steps, you're already in position to launch depth conversion computations. Select your outputs and run. Very quickly, you're able to visualize your scenario outputs in Petrel. For example, this is your depth map for layer 3 associated with quantified uncertainty. You'll see that many other outputs have been computed and stored in your Petrel project. Now let's create a second UDOMORE Depth scenario with custom parameterization. Simply copy scenario 1, rename it, and you're ready to go. The first step is to address uncertainty on your 2D time interpretation maps. The sigma value corresponds to time interpretation uncertainty. You may enter a constant sigma value corresponding to time uncertainty that is constant in space. You may also enter a variable sigma value corresponding to time picking uncertainty that varies in space. In this case, you must upload a time picking uncertainty map from Petrel. Spatial range values correspond to the sigma correlation distance. You may enter an isotropic range if you're considering the same correlation distance in every direction. You may enter an anisotropic range if you are considering different correlation distances for the two main directions, and an azimuth to fit the geology of the target you're working on. Spatial continuity corresponds to the variogram model applied to the correlation distance. You may consider cubic, exponential, or spherical variogram, depending on the structure you're working on. The second step is to address uncertainty on your well tops. You may enter a constant uncertainty value corresponding to uncertainty on well tops that is constant in space. You may also enter a variable sigma value corresponding to uncertainty on well tops that varies in space. The third step is to address uncertainty on velocity function residuals. Similarly to work performed for 2D time interpretation maps, you're able to enter sigma, spatial range, and spatial continuity values. The fourth and final step is to address parameterization of your velocity model trend and its associated uncertainty. Layer 1 is very homogeneous and mainly filled by sandstones, so we can adjust the V0 parameter accordingly. Layer 2 shows strong correlation between seismic velocities and well velocities, so we can adjust the A parameters to the correlation coefficient. Layer 3 shows a linear compaction with increasing depth, so we can adjust the V0 and K parameters to fit with compaction laws visible at each well. Following these 4 additional steps, you're again in position to launch new depth conversion computations. Simply select your outputs and run. Now let's compare the results of the 2 scenarios. These are the depth maps resulting from the 2 scenarios. There is a plus or minus 10 meter difference between both maps at the target area, which in this case, because we're dealing with a thin reservoir, strongly impacts volumetrics predictions. In this tutorial, you've learned how to get started with UDOMORE depth, preparing input data, configuring and optimizing your UDOMORE depth scenarios, selecting outputs, and visualizing them in Petrel. You're all set. For additional support around UDOMORE depth, simply call SaySquare. We can help you with online or on-site support for increasing your learning curve and maximizing benefits.